And they discovered that these tiny particles are rich in the seeds of life.
When you look at them in an electron microscope, it's this wonderful array of minerals and carbon and organic materials that are 4.55 billion years old, and we believe are the building blocks of life.
And this extraterrestrial dust isn't the only possible source of life's ingredients. In a region of space called the asteroid belt are huge amounts of debris left over from the formation of the solar system. And sometimes, chunks of debris containing metal and rock fall to Earth, bearing surprising gifts. One such meteorite landed in the town of Murchison, Australia in 1969.
It's a gold mine, this little chunk of meteorite which fell on Australia last year. For the past 6 months, they've been taking it apart and have discovered it contains amino acids, the building blocks of life.
It was the first time that complex organic compounds had ever been found in material from space. And if meteorites like it were common, perhaps they had delivered vast quantities of the original constituents of life to early Earth.
Enough organics are present here that we think that meteorites like this provide to the early Earth its entire budget of organics. So all the organics in your body, all the carbon in your body, and in your lunch you had today, arrived on the Earth in meteorites like this. If they come in the atmosphere in large enough objects, they're like little capsules coming in the atmosphere. They break apart on the Earth's surface and deposit their cargo of organics.
More than 70 kinds of amino acids have been found in meteorites. And many are the fundamental ingredients of proteins that make up living cells. During the heavy bombardment, millions of meteorites may have seeded the Earth with the stuff of life. And there might have been an even more efficient delivery system. Comets are like giant dirty snowballs made of ice and rock. Some comets that hit the early Earth were the size of mountains, and a large portion of their mass could have contained organic compounds. The destructive power of comets and meteors is astronomical. The meteor that slammed into Earth some 50,000 years ago, here in Arizona, blasted a hole in the ground nearly a mile wide, from here to here, and so deep it could hold a 60-story skyscraper. And as if that weren't enough, the force of the impact was so great that it instantly vaporized nearly the entire meteor. 300,000 tons of it. So it makes you wonder, if the building blocks of life were delivered courtesy of comets and meteors, could any of the tiny ingredients they carried have survived the landing? And just what happens to things like amino acids when they slam into Earth with such devastating power? To answer those questions, one scientist came up with an ingenious experiment. Using a huge gas-powered gun,
That's good, stop.
Jennifer Blank simulates the extreme pressures and temperatures that are unleashed when a comet smashes into Earth.
We set out to test whether or not the materials would survive or whether they would break down. And we expected that, or we were hoping that some fraction would survive. And we figured the parts that didn't survive would break down into smaller components. But in fact, what we found was much more exciting.
The gun fires a bullet at 5,000 miles an hour towards a sample that represents the organic molecules inside a comet. The sample consists of a solution of 5 different amino acids, 2 of them present in every living cell. The mixture is inserted into a steel capsule. The gun will send a shockwave through the capsule, simulating the extreme pressures of a comet's impact.
I think it's very hard to just imagine what kinds of pressures were generating these experiments. If you think about going to the bottom of the ocean, the pressures you'll have there are only 100 times atmosphere. So these are hundreds of thousands of times atmospheric pressures.
Will Jennifer Blank's experiments show that the building blocks of life can survive a crash landing on Earth?
Clear the room.
Okay, charging up. Okay, bringing up the X-rays. Okay, I'm going external group. Ready to fire?
Go ahead.
Okay, then 3, 2, 1, fire. 3, 2, 1, fire.
When they remove the capsule, it's undamaged. But have its contents survived the impact? The once clear solution of amino acids has turned a tarry brown color. And the analysis revealed that not only had the material withstood the colossal pressure of the impact, but it had transformed into a new compound. Amino acids, combinations of carbon and other basic elements, had fused together to form more complex molecules called peptides.
We went from our initial small compounds, and here's an example of one of them, simple amino acid, and we used the energy associated with the impact to build larger molecules. Molecules like this. This is a peptide, and we showed that we could use the impact energy to grow larger molecules from the simplest building blocks of life.
Peptides link together to form larger building blocks, proteins, which make up all the cells in our bodies. But the leap from non-living ingredients to a living creature, complete with DNA which allows cells to replicate, is staggeringly complex. No one knows how this process started or what course it took.
It is hard to really get your head around the great leap from non-living to living.
Well, it's hard enough that nobody's succeeded in doing it in the laboratory.
I think it's an astonishing mystery and one that we truly don't understand in any great detail.
While we don't yet know how the spark of life occurred, we can try to figure out where it might have gotten a foothold. And because the planet was under such devastating assault from comets and meteors, the leap to life may not have taken place up here on Earth's surface. To take hold, life might have needed a safe haven, perhaps underground. A team of scientists descends into one of the deepest mines on Earth to investigate whether microbial life can survive far below the Earth's surface.
And the mining environment gives us this fantastic window into the deep subsurface. It's a unique scenario because there is nowhere else on planet Earth that allows you to have access to that sort of sample location at 2, 3, 3.5 kilometers deep.
It takes 45 minutes to reach the heart of this South African mine. Conditions here are extremely uncomfortable. For humans, that is. The temperature of the rock is 120 degrees Fahrenheit, and the air pressure is twice that at Earth's surface. Life down here survives entirely without sunlight. If they exist, microbes need to find a way to live in pitch darkness, drawing chemical energy from water and minerals trapped in the surrounding rocks.